For many developers, the mid-level plateau is a difficult trap to escape. Adding code to mature architectures with clear requirements is safe work, but being asked to design a highly scalable system from the ground up requires an entirely different skill set. Moving into a senior engineering role requires stepping away from localized coding habits. Companies compensate senior engineers for their ability to design high-level architectural trade-offs based on very rough requirements. The primary target in this transition is the single point of failure. If one isolated component can crash your entire application, the architecture is inherently flawed. To understand how these components interact, we are going to build a production-ready system from scratch. We will establish a single node baseline, then systematically scale it horizontally by layering in networking, databases, APIs, and security protocols. Mastering these concepts is the exact barrier that separates a developer writing localized code from an engineer architecting distributed systems. Our baseline is a single server. A user's request hits the DNS, routing traffic directly to our box. Zooming in reveals TCP, initiating communication with a strict three-way handshake: synchronize, acknowledge, and establish. This handshake secures guaranteed delivery. Dropped packets are automatically resent and sequenced perfectly. Compare that to UDP, which skips the handshake. It fires a continuous stream of packets. If one drops, it is permanently lost. UDP sacrifices reliability to achieve maximum speed. That trade-off makes it the necessary choice for stateless, real-time streaming like video calls, where dropping a frame is acceptable, but waiting for a delayed packet would ruin the feed. Even at this basic single-server scale, the choice between strict delivery and raw speed physically dictates the baseline capabilities of the application. As our user base grows, a sudden traffic spike will overwhelm this setup. The single server hits its maximum capacity, the CPU bottlenecks, and the entire system crashes. We could upgrade this machine with more RAM and CPU cores, but this approach, vertical scaling, eventually hits a hard physical cap, and it offers absolutely zero redundancy. The required solution is horizontal scaling. Instead of building one massive machine, we clone our server into a cluster of 3 identical nodes to share the computational load. This introduces a new architectural problem. When thousands of clients send requests simultaneously, how do they know which specific server to communicate with? We introduce a load balancer. Acting as middleware, it intercepts incoming client traffic and actively distributes it across available nodes. The simplest distribution logic is the round-robin algorithm. It routes traffic sequentially across the cluster, which works well if all servers have identical hardware and process uniform requests. If the application handles highly variable session lengths, we use the least connections algorithm instead. The load balancer actively monitors the cluster and directs mute traffic to whichever node currently holds the fewest active connections. This hash ring visualizes a third strategy, consistent hashing. Here, a mathematical function maps an incoming client IP address to a specific point on the ring, cleanly routing that user to the closest server node located on the same path. Consistent hashing ensures that a specific IP address consistently hits the exact same server. This is vital for maintaining sticky sessions, where local state and temporary data must be preserved for a user across multiple requests. By clustering the web tier and routing traffic, we successfully eliminate our first single point of failure. However, as traffic scales, that pressure immediately shifts further down the stack to the data layer. In our current setup, each web server contains its own internal database. If a server goes offline, that specific data becomes inaccessible. The database has become the new bottleneck. To solve this, we decouple the storage. We extract the database from the individual web servers and consolidate it into a distinct standalone data tier. Moving to an independent data tier forces a critical architectural choice between 2 paradigms: relational databases, known as SQL, and non-relational databases, known as NoSQL. SQL operates on strict schemas. Data is locked into a rigid grid of tables and rows. If the system needs to link a customer to their purchase, it executes a complex join operation across the users and orders tables. SQL enforces rigid data integrity, guaranteeing that a transaction either completely succeeds or completely fails. This makes it mandatory for financial ledgers, banking apps, and inventory systems. NoSQL abandons tables for flexible document stores and wide column structures. It dynamically absorbs varied, unstructured data points without requiring predefined schemas. By bypassing the overhead of strict constraints and table joins, NoSQL achieves massive read and write speeds. It is optimized for social media feeds and recommendation engines, where low latency is prioritized over strict transactional consistency. Selecting a database tier is a matter of aligning a paradigm's specific strengths with the system's underlying operational constraints. With the server scaled and the data decoupled, we must optimize the API layer, the strict contract dictating how clients interact with our backend. The industry standard architecture is REST. It utilizes a resource-based approach, mapping HTTP methods like GET and POST to specific endpoints. But REST introduces a severe latency bottleneck in complex systems. To populate a single view, a client often has to make multiple separate requests to different endpoints, waiting for sequential, bulky response blocks, and overfetching data it doesn't need. GraphQL was engineered to solve this network inefficiency. Instead of hitting multiple endpoints, the client collapses the request into a single endpoint. It sends a payload defining the exact data schema required, and the server returns a perfectly matched response. REST is highly effective for predictable resource mapping, but for complex, deeply nested user interfaces, GraphQL avoids wasted bandwidth. Optimizing this API paradigm directly reduces round-trip network latency, an absolutely critical requirement when serving millions of mobile clients on unpredictable connections. Our horizontally scaled system now contains a hidden security flaw. Traditional applications track users through stateful session memory, but if our load balancer routes a user's second request to a completely different node, that node has no memory of their login. We could deploy a centralized session database, forcing every server to check it to verify identity on every request, but that immediately reintroduces a latency bottleneck. The scalable solution is stateless authentication, commonly handled through JSON Web Tokens, or JWTs. When a user authenticates, the server generates a JSON object containing their data, applies a cryptographic signature, and hands this token back to the client. The server then retains zero memory of it. For all subsequent requests, the client attaches that token. The server verifies the cryptographic signature locally. If the math clears, the request is validated, entirely bypassing the database. It is critical to differentiate two concepts here. Authentication verifies who the user is, often using protocols like OpenID Connect. Authorization verifies what permissions they have, using frameworks like OAuth 2 or role-based access control. True distributed systems require that stateless identity verification remains entirely decoupled from access control frameworks. Taking a macro view of our complete topology, we see the results. Client traffic routes through a load balancer, distributes across a clustered API layer, authenticates statelessly, and efficiently queries a decoupled data tier. By systematically identifying and extracting bottlenecks, we have engineered out every single point of failure, creating an architecture capable of accommodating massive user bases. In a live production environment, we would complete this topology by placing rate limiting and web application firewalls in front of the load balancer to filter out DDoS attacks and malicious traffic. Transitioning to senior engineering is strictly about the mastery of these high-level architectural trade-offs. Building at this scale requires total command over how data moves, replicates, and is secured across physical networks.